Good afternoon, everybody. My name is Mark Kirby. I'm the Industry Training Manager with the University of Waterloo's Multi-Scale Additive Manufacturing Laboratory. And I'm going to spend the next 15 minutes trying to convince you how we can all learn from failure. So what do we mean by failure? What do I mean by failure? I do have a penchant for rockets, and I'm going to use rockets and aviation in general to frame a lot of the discussion around success and failure. So here it's fairly easy for us to recognize this is a catastrophic failure. This is an Antares rocket. Clearly this is catastrophic. We've seen some spectacular failures recently. SpaceX have provided us with a number of these, and critically they seem to have learned quite quickly from these failures. However, generally catastrophic failures like the Challenger or Columbia space shuttle tragedies are very damaging to programs, and despite the lessons learned, they set those programs back massively. So I'm not advocating catastrophic failure as a productive way to learn versus learning from small failures. Well, if we've looked at catastrophic failure at one end of the spectrum, what does success, what does perfection look like? Is this rocket launch a success? Was it perfect? I'm going to argue that no process, person, organization is ever perfect. We always have small deviations from nominal, but the challenge is one of continuous improvement, striving for perfection, and critically learning to see failures and having a process to record them and to share them is how we will productively learn from small failures. Exactly how something fails can tell us a great deal about it, about its material properties, that we can never learn from just looking at the outside of a component. However, since I'm not a material scientist, I'm not going to be spending much time today looking at the impact of material properties on the failure modes of additively manufactured components. However, sensing the disappointment if I don't talk a little bit about material failures. Here is an example from a 2020 Penn State paper where we have a vocabulary to describe process flaws and a taxonomy, and we're going to need exactly these kinds of things, a vocabulary and a taxonomy to describe all levels of failure in additive manufacturing. So I said earlier I was going to use aviation to frame a lot of this discussion. And if we look at failure in aviation, in the early days, back in 1903, nearly 80% of failures were machine related, whereas today, nearly 80% of failures in aviation are human related. We're going to find the same is somewhat true in additive manufacturing, where our state of evolution is probably between these 2 points. So building on the previous slide where we saw that 80% of aviation accidents are human related, here Siemens saying that potentially 80% of additive build failures are due to incorrect build orientation and or support strategy. And they have a software solution for this, and just as aircraft may have some very sophisticated software solutions, still oftentimes it's humans that are doing this. So maybe we have an 80% human related failure cause here, which is build orientation and support. So let's have a look at that in a little bit more detail. So to make this real, let's have a look at this 80% of build failures or small failures may be related to orientation or support. So this is an example from a dais. It's a medical device. The build orientation is as shown in this image here on the left. Up is the build direction, and we have a fairly organic shape, and then we have a prismatic shape. After it's been printed, the rectangular shape here has some distortion, and this turns out to be unacceptable. And the question is, this is a small failure, it's not catastrophic, but the question is, what was the cause of this distortion? So what we've done here is to use simulation with a nominal 50mm, 1 mil thick tube that's tipped over at an angle, and this is the result of the simulation. This is using Autodesk Fusion. And we can see our eyes automatically drawn to the area of maximum distortion here. The distortion's been exaggerated by a factor of 20. But really the distortion we're interested in is the opening of the aperture at the bottom here. And it's still somewhat difficult to kind of see what's going on. Number one, is that distortion what we saw? And even if it is, what was really the root cause? So let's have a look at this sort of temperature evolution over time, which can often tell us a lot about the root cause. What we can see here is that the tube, because it's been tipped over, the corner of the tube at the bottom becomes very hot earlier on because all of the heat has to flow through that small area, and that's really the root cause of the distortion. And if we want to fix the distortion, we probably need to orientate that tube normal to the build plate. So here we're using simulation to inform the root cause for the failure. So this is an example. It is actually a support failure. It's not orientation as such, but it's support failure, where the build had been produced subscale successfully, and then we'd come to do a full scale build, and here the support structure, which is what you can see here, has actually moved during the build and redistributed powder. You shouldn't normally be able to see any support structure sticking up like that. And if we have a look at what went on when we were built full scale from this video here, we'll see what happened at full scale. The component became very tall and flexible and vibrated. So we had a failure at full scale when the support became structurally unstable. So continuing on our theme of 80% of failures may be down to orientation or supports, let's have a look at another one. This is going to be down to supports again. Initially we built the part subscale. This is a reduced build volume, about 100 millimeters across. We have a prismatic structure here, and it's supported by a gyroid lattice. This built okay. We also built two sample lattices here. These are called Voronoi lattices. They also appeared to build okay. So we went ahead and went full scale. This is now 250 millimeters across, but we also replaced the support structure underneath this table with the Voronoi lattice, and you can see now in this build here, this is what an unhappy build looks like. These parts sticking up, cuts to the recoater. The structure is very unhappy, and indeed we had to stop this fairly early on because the Voronoi lattice, while it appeared to be okay at this scale here on the top right, by the time it was scaled up, overhangs that maybe were only 1 or 2 millimeters here had now become 4 or 8 millimeters, and the part was very unhappy, as you can see. We're going to continue here with the joy of lattices. So we're still building this same structure we were looking at in the previous slide. This is still 250 millimeters across, but now we've replaced the Voronoi lattice with the gyroid lattice. But fairly early on in the build, we're seeing some cuts appear in the recoater. This line here, the recoater is moving from top to bottom in this direction. This is a cut in the recoater. So immediately went and looked at the data that we had, what the build file, and saw unfortunately that the lattice is unsupported at the edges. It's just the way it's been truncated here. And so these islands that are arrowed are completely unsupported areas, and that's a no-no in laser powder bed. And you can see this is the result. This is as far as the build got with these unsupported islands. So called it 50 shades of gray and 50 gig of data as well. These lattices can become computationally very intensive, and that can be problematic. And also, if you look very carefully, you can also see the lattice is not completely joined properly to the prismatic body. That can also lead to some failure. So there are some sort of interesting organizational issues that can, organizational and computational issues that can come up with lattices. Earlier on, if you remember, we talked about in the early days of aviation, maybe 80% of failures were down to the machines. And this particular failure, I think, sort of illustrates how additive is maybe somewhere in between those early days of aviation and the more mature aviation industry we have now. So we came in to find the machine in this condition where there's a lack of powder all at the front here. This is a catastrophic failure. And it's not that we're actually out of powder. There is still powder in this hopper here. But what's happened overnight is the overflow system of the machine has filled up, leading to an accumulation of powder in the corners of the machine here, which has prevented the mechanical dosing action of the machine. It needs to push on these plungers here in order to dose powder out of the hopper. So the machine, while it still has powder in here, hasn't been able to actually dose powder correctly. So we've had a failure, and we could argue that maybe this is down to human error, that the operator shouldn't have let the overflows fill up overnight. Of course, that's easier said than done. Or we could look to the future and say more modern machines in a more advanced state of evolution will automatically recirculate powder, and failures like this will become rare. Okay, let's just finish up. Remember, we said that maybe 80% of failures are down to support or orientation. I'm going to argue this particular failure is maybe down to orientation. We're necessarily building some tensile bars that are orientated horizontally. At the end of this particular slice, everything looks fine, but on the next slice we can see here something's definitely gone wrong in this corner here. And in fact, what's happened is the bolt in the corner here of the substrate has actually sheared off and caused all of the powder to vibrate up, redistribute itself. So that's a catastrophic failure. So one of the questions with a failure like that is, was that down to a machine error? Should the bolts have broken? Or is it down to orientation and the bolts were overstressed and they would never have held up? So we can use simulation, and again, this is using a NetFab simulation after the fact to look at what the stress distribution is like. And in fact, we can see in the corners of the build plate here, the stresses are indeed predicted to be unexpectedly high. So the solution here was to use higher strength bolts, and then if it was still further strength improvement was needed, to use a thicker substrate. So far it seems that all we've done is look at failure. We haven't learned from failure. So I'd like to look here at the work of the cognitive psychologist Manu Kapoor, who talks about how productive failure can be used in a system he calls design of learning to improve outcomes. One of the thought experiments Manu has is, let's imagine we have a toy to give to a group of children. We split the children into two halves. In the first half, we explain how to play with the toy, and then we give the children the toy. And the second half, we just simply give them the toy. And the question is, which group do we think will play more creatively with the toy? And most people would say it'll be the half that have not been shown how to play with the toy. Now, this is not the way that we teach normally. We normally give knowledge first, so it's direct instruction. The other thing we need to do as well is we need to get people ready to see. An expert will see things that a novice will not see. So all of this can feed into a design of learning where we set people up to learn more effectively. So for additive, we've talked about how supports are so important, but maybe rather than explaining all of this, maybe the first thing we do is we simply run an experiment. And we build 3 disks with no supports underneath them at all. Here they are. And then maybe we get people to reflect on what happened and why that happened. So I think productive failure is a great way for us to get deeper understanding and more transfer. The question is, how do we use additive manufacturing, I'll call it safely, for people to experiment? Should it be with real builds? Should it be with simulation? Software is probably the lowest risk and lowest cost way to allow learners to explore this new toy and to be as creative as possible and come up with new solutions, new orientations, new support structures, ultimately leading to a much deeper understanding of the process. So how do organizations learn from failure? This is an example in the medical device industry where after the build, cranial plates are being polished by humans, and the polishing is actually going right through the entire cranial plate. And the fundamental reason is that the cranial plate is actually too thin to sustain polishing. In a regulated industry, the first step after a failure like this would be to record the failure as a non-conformance and then to conduct a risk assessment to decide on corrective action. With a relatively new technology such as additive manufacturing, it's unlikely that all of the failure modes will be known ahead of time. So it's important that failure modes effects and analysis matrix is a living document, and failures are fed into this and root causes examined to understand whether mitigation strategies or process improvements need to be developed depending on the risk associated with the failure. In this case, for the cranial plate, a new step was inserted into the work process to inspect the thickness of the device and ensure that no areas were too thin for subsequent downstream processing. So how can we all learn from failure as a community? Well, there are some efforts underway already in social media, Pound AM WTF with Tim Simpson and Pete Zielinski posting failures. We also have a series of webinars from GE and Siemens and others, and also just random posts on social media where somebody's come across a failure and is asking for advice. So right now we have the beginnings of sharing a failure, but what we really need is a more holistic way to bring all of this together. I would hope, again, coming back to my aviation theme, that we can learn from the aircraft industry and we can report incidents, not necessarily accidents, catastrophic failures, but just incidents. This is an example from the NASA database, and it has over 113,000 incidents reported over a somewhat 20-year period. And again, these are categorized by phases of flight, so this could be to do with the build process if we're talking about additive, and again where the root cause potentially was in the problem. So I would hope that we can develop a system like this for additive manufacturing where incidents can be openly reported and shared, and we can develop new boundaries to make the process safer and better for everybody. Thank you very much. I hope some of you may have some questions or want to send me an email to my email address on the screen. Maybe my audience participation question right now would be in the background, that very artistic image, who first posted that on LinkedIn and what exactly is going on.